Section 16, End of the Universe, Big Rip. Cosmologists do not know for our universe whether dark energy's W value is exactly -1 to a high degree of certainty, which would be constant dark energy density, a cosmological constant. They also do not know whether the curvature of our universe is exactly 0, flat. If the curvature of the universe is exactly 0, then W is probably in the range -1 to -1.06. If W is exactly -1, then the curvature of the universe is either 0 or negligibly small. But if W is not -1 and curvature is not exactly 0, it is difficult for cosmologists to determine the exact values. You might see the term quintessence for W different than -1 or for any time-varying dark energy. If W is more negative than -1, even by a small amount, the universe will have a different end, called the Big Rip. W being more negative than -1 makes the power of the scale factor for the dark energy term become positive in the Friedmann equation. This speeds up the expansion of the universe and the acceleration, and it increases the dark energy density of the universe with time in the future. This case is sometimes called phantom dark energy. Here we see the expansion of the universe for different values of W for dark energy for the next 140 billion years, 10 times the present age of the universe. The vertical axis is the scale factor from 1 to 1,000. If W equals -1, the blue curve, constant dark energy density, we get the Big Chill. If W is more negative than -1, the red and purple curves, we get the Big Rip and faster expansion of the universe than the exponential for the Big Chill. We'll talk about the Big Rip next and the Big Crunch later. This is a representation of our local group of galaxies, with the Milky Way and Andromeda being the largest galaxies of the 80 galaxies in the local group. Surprisingly, the average matter energy density of our local group is only about twice the present energy density of dark energy. So a very good vacuum with some overdensities, which are the galaxies. We are fascinated by the galaxies, but tend not to give much of any thought and appreciation to the vast volume of near vacuum in intergalactic space. Here is a table of the matter energy density of nearby astronomical objects. The third row is for our local group of galaxies, about 2.3 times the present energy density of dark energy. The matter energy density of the Virgo supercluster, of which our local group is a part, seems to have slightly less matter energy density than dark energy presently. Earth is an overdensity of our solar system, which is one of trillions of overdensities in the Milky Way galaxy, which is an overdensity of the local group, which is an overdensity in the Virgo supercluster and in the universe. If W is more negative than -1, then the energy density of dark energy increases with scale factor, So with time. Once the energy density of dark energy and the universe reaches the energy density of galaxy clusters, the galaxies will no longer be gravitationally bound in the cluster, and the expansion of space will then occur between nearby galaxies, not just between distant galaxies. Any superclusters that had been gravitationally bound will no longer be bound. If W equals minus 1.03, then the dark energy density will grow to the present density of our local group of galaxies at a scale factor of around 9,000. This will occur around 128 billion years from now, long after the Earth is vaporized and our Sun is a very old white dwarf. However, our data for the universe is not good enough to predict this far, and my simulation is not precise. At that time, the scale factor for the W equals minus 1 big chill case would only be 1750, 5 times smaller. In both scenarios, galaxies beyond our local group will no longer be visible from here in visible light. The time for separation of our local group of galaxies is very sensitive to the value of W, which is not known precisely. For W equals minus 1.06, separation occurs around 64 billion years from now, at a scale factor of 95. For W equals minus 1.01, separation occurs around 387 billion years from now, at scale factor around a trillion. For W equals minus 1.001, separation occurs around 3.9 trillion years from now. However, the galaxies of the local group are all expected to coalesce to a single galaxy between 100 and 1,000 billion years from now. So there is a race between coalescence and the Big Rip. And to repeat, if W equals minus 1 exactly, expansion of the universe never separates the local group of galaxies. Once the energy density of dark energy and the universe reaches the matter energy density of galaxies, millions of times more dense than dark energy today, I believe the stars and dark matter in the outer galaxy will no longer be gravitationally bound to the galaxy, and the expansion of space will now occur between those stars, not just between galaxies. The Big Rip expansion of the universe will release stars from their former galaxies, starting in the outer regions and progressing rapidly to the core of the galaxies. If W equals minus 1.03, then the dark energy will grow to the density of the Milky Way at a scale factor of around 10 to the 68. And stars will escape their galaxies. This will occur around 383 billion years from now. There may be young stars shining at that time, and old red dwarf stars will still be shining, but old brown dwarf and white dwarf stars would be very dim or no longer shining. Our galaxy will probably be much dimmer then than today. Black holes will still exist and not have evaporated by then. After another 300 million years, the scale factor will exceed 10 to the 250, and any planets in solar systems will escape from their stars. An hour later, planets and stars would be ripped apart. Immediately thereafter, molecules, then atoms, then nuclei. Thus the name Big Rip. Such a universe has an end of time at which the scale factor becomes infinite. None of this happens for the Big Chill, which may continue for trillions of years if the model is correct. I don't think physicists know whether the Big Rip would rip protons and neutrons into quarks, but that doesn't matter much as we can consider this possible end to our universe hundreds of billions of years from now. The Big Rip ends with an infinite density of dark energy, a radiation temperature of 0, and an infinite scale factor at a finite time, the end of the universe. Whereas the Big Bang started with an infinite density of radiation and matter, an infinite radiation temperature, and a scale factor of 0. However, new physics is needed anytime some value is said to be infinite, and it could be that a Big Rip phase halts at some maximum energy density and ends with a Big Chill. The time for the Big Rip end of the universe is very sensitive to the value of W, and increases without bound as W approaches -1. Cosmologists would like to know W more precisely, of course, but they may never know it sufficiently well to rule out Big Rip in favor of Big Chill. But the better they can constrain the value for W, the better they would know the time scale for Big Rip diverging from Big Chill. The Standard Model says that dark energy has constant density and W equals -1 exactly, and the universe will end with Big Chill, but that is only probable, not certain. No cosmologist can tell you definitely how our universe will end, but our galaxy will not be ripped apart for the next 180 billion years.